welcome to another lecture on molecules in motion. Last class, if you remember, we had introduced the concept of transport numbers or transference number, and we had talked about how transport number can be obtained by various means. Whatever expressions we had derived so far in terms of the mobility, in terms of the molar conductivity, in terms of the ionic speed, we could relate each of these parameters with the transport number or transference number. Transference number, what we have described was the ratio of the fraction of, it was a fraction, it is the ratio of the current carried by the one type of ions, which is positive or negative, divided by the total current which is carried through the electrolyte system. So, the various expressions which we had derived in the last class was, this is the definition of the transport number. When I have plus minus, I individually mean the contribution of the plus ion and the negative ion. When I say this is not, that means I am finding out the transport number under limiting conditions of 0 concentration of the electrolyte. So, if I have this definition, from this definition what we derived in the last class was the various expressions of the transport number or transference number in terms of the molar ionic conductivity, the ionic mobility and the ionic speed. So, this is, if you remember, this is the transport number for any type of positive or negative ion. Remember, we had talked about the condition where we have only one type of electrolyte, not a mixture of electrolyte, one type of electrolyte giving only one type of cation and one type of anion. Okay? And from that expression we had derived the expression for how that can be related to the ionic conductivities of each of the ions, and this was the molar conductivity of the electrolyte at infinite dilution. This was the ratio which we had seen for the positive and the negative ion. Similarly, the ionic mobility of the ions, individual ion plus and minus, divided by the total ionic mobility of the plus minus ions in the solution. Similarly, the ionic mobility of either plus or the negative ions is going to be equal to the speed of the ions at infinite dilution, obviously, when we have the total the speed of the positive ion divided by the speed of the positive and the negative ion in the system. So, this plus minus represents, we can expand this to either positive charge or to the negative charge. Denominator always is always the summation of the two ions, which whatever the property may be, either it is ionic mobility or the speed or the molar conductivity of the electrolyte. So, now we have also talked that these parameters are measurable parameters. So, we can if we want to find out, say, the ionic mobility or ionic conductivity or ionic mobility of the ions, we can do that if we have the knowledge of the transference number at infinite dilution of the solution. We have taken infinite dilution of the solution so as to avoid the interionic interactions between the ion, which complicates any relationship which we have derived so far. So, there are two types of method to measure the transport property, and the two most famous accurate methods are, one is the moving boundary method and the other one is the Hittov's method. We are going to discuss each of the measurement methods of transport numbers or transference numbers. Now, before doing that, what we need to understand, if I have 1 mole of the electrical charge is passed through the solution of electrolyte, then through every plane that is perpendicular to the current path, you have T plus moles of charge are carried by the positive ions and T minus moles of the charge carried by the negative ions. Am I clear what I am trying to say? If there is 1 mole of electric charge passed through a solution, okay, 1 mole of electric charge is passed through the solution and the solution is composed of one type of electrolyte giving rise to one type of anion and only one type of cation, then through if 1 mole of the charge electric charge is passed through the solution, then through every plane that is perpendicular to the path of the current, we have T plus moles of charge carried by the positive ion and T minus number of moles of the charge carried by the negative ion. What is the T? T is the transport number of the positive ion and T minus is the transport number of the negative ion. Okay. So, each mole of a positive charge, suppose we have Z plus as the charge of positive charge, mole if each mole of a positive charge Z plus to pass T plus moles of charge would require how much? We will require the passage of T plus divided by Z minus moles of positive ion. Is that clear what we are trying to come to? Each mole of the positive ion, suppose it carries a if the positive each positive charge is represented by Z plus moles. So, each mole of positive ion, if it passes, if I say T plus moles of charge would be passed, then that would require T plus by Z plus moles of the positive ions. Similarly, to pass T minus moles of charge would require the passage of T minus divided by Z minus moles of the negative ions, where T plus is the transport number of the positive ion and T minus is the transport number of the negative ion. Okay. So, I hope this is clear. Each mole of the positive ion carries Z plus moles of charge. So, to pass Z plus moles of the charge would require the passage of Z plus by Z T plus by Z plus moles of the positive ion and T minus by Tz moles of the negative ion. Okay. So, this will be more clearer when we talk about the Hittov's method. Now, let us first look into the moving boundary method. As the name suggests, in this method the motion of the boundary of two ionic solutions have a common ion is observed as the current flows through the solution. So, what we have? We have two ionic solutions where one ion is going to be common, either the cation or the anion. When we are trying to find out the transport number of a cation, then we usually take the anion to be as the common ion. Okay. So, if I have a salt which is of interest, say M plus Z minus X minus of molar concentration C. Okay. If I have we want to find out the transport number of the ion M plus and the salt which we are taking is M plus X minus has a concentration molar concentration of C. Okay. Now, see what we are saying, we have a the method where motion of the boundaries of two ionic solutions are into consideration when we have a flow of current through the solution. Okay. And here we have taken the common ion to be a anion and the two cations are M plus. We can represent them as the one which is of interest, for which we want to find out the transport number. Another solution which is another ionic solution is the N plus. Okay. So, we have two solutions, two electrolyte solutions that have one common anion that is Z, that is X. Okay. So, two ionic solutions salts are, this is one, and let us Nx be the other. Mx is one and Nx is the other. What we are going to see? We are going to see the motion of the boundaries between the two ionic solutions with that we have. And these two ionic solutions which we are having is, one is Mx and one is Nx. Which is of interest, for which we want to find out the transport number? Let that be M. Okay. Now, the condition is that we have a common ion. Since we are interested in finding out the transport number of the positive ion, so let us keep the, what we have kept, the N ion as the common. So, X is the common ion between the two salt solutions which we have, Mx and Nx, and Mx is the one of our interest, and that is of concentration, molar concentration C. Okay. Now, the solution of the Nx is called the indicator solution. It is of denser, its density is going to be higher, and if I have a tube like this, I have Mx here, I have Nx here, and I have the boundaries demarcating. This is we are saying this is at the 0 condition, and 0 condition I have at this position where I have only the Nx, and here I have the Mx. Okay. So, the lower portion of the vertical tube with cross section area A will contain the Nx. Okay. And that is going to be the indicator solution, and indicator solution will have a higher density compared to that of the lead solution, which is of Mx. Okay. So, and this ion is of our interest. Mx, the M ion is what, for which we are finding out the transport number. We are finding out the transport number of the M ion. Okay. So, what we are looking into, we are trying to find out the transport number T T plus, and this T plus is corresponding to the transference or transport number of the M cation which we have in the solution system. So, the solution of the salt Mx, which is the lead solution, occupies the upper portion of the vertical tube of the same cross section area. So, what we have this as the common area which we will be looking into. So, there should be a sharp boundary between the two liquids Nx and Mx. The indicator solution is this, that is Nx is denser than the lead solution is the Mx, and one more thing needs to be kept in mind, that the mobility of the ion of interest should be greater than that of the indicator of the cation present in the indicator solution. Okay. So, the indicator solution, the cation is N, and the lead solution and of our interest for which we are looking into the transport number is M. The mobility of M should be greater than that of the N. So, what is the criteria? That the Mx solution, which is the lead solution, which will be in the lower part of the tube, should have a higher density compared to that of the leading solution of Mx, where M is the ion of interest for which we are trying to find out the transport number, and of these the M ion is supposed to have a greater mobility than that of the N ion in the solution. Okay. If M ion, what will happen is, if M ion diffuses into the lower solution, they can be easily pulled off very rapidly compared to that of the N ions around them, and form a sharp boundary, reform the boundary again. So, suppose I have a current I passing through the solution. This is the column which I have. If at delta time t, the boundary moves from A to CD. So, what is our interest in the volume? Our volume of interest is AB CD. This is the volume of interest. Okay. So, what happens? The mx is going to diffuse into the solution, and then what happens is the as we move from AB to CD, the whole volume, then what happens? Ma plus ions, the M plus ions in the if it comes into the volume elements, that means it has crossed this boundary CD. Okay. So, what we have next? What we are going to monitor? We are going to monitor when we are passing a current of I in delta time delta t, then when the boundaries this is going to move into this, that means it is crossing the CD boundary. We are looking into the number of ions which will be present in this volume A, B, C, D. Okay. So, the distance moved by the boundary is observed as the current is passed. Okay. All the Ma plus ions in the volume element, which is A, B, C, D, must have passed through the CD barrier to move into this zone. Okay. What is usually done? One of the procedures is you use bromothiol thymol blue indicator to the slightly alkaline solution of the Ma plus ion of interest to use use a cadmium electrode at the lower end of the vertical tube. So, we have a cadmium electrode in the lower end, and we have added bromothiol thymol blue indicator into a alkaline solution of this. Now, the electrode which we have placed in the bottom is a cadmium electrode, and the cadmium electrode will produce cadmium plus 2 ions, which are slow moving and they are slightly acidic. So, I have the alkaline solution where you have the indicator mixed into the salt solution of Mx, and what happens? The cadmium ions generated from the cadmium electron move slowly, and these are acidic slow moving ions, and when they move when they come in contact with the Ma plus ion, which is having the indicator bromothermal blue, they will have a color change. So, this will be indicated as a color change when we see the boundaries. What we have looking into now? We are looking into this zone. This is the zone which we have, in which you have what will be the concentration of the number of ions of Ma which is going to be present here. The total number of ions which is going to be present here will be the concentration of the ion electrolyte, will be the concentration of the plus ions of the solution into the total number of into the Avogadro number. The concentration into the Avogadro number will give you the total number of ions in the volume element. This is the L, and this is, if the cross section area is A, then the volume element is going to be L into A. So, the total number of ions in this will be L into A into the molar concentration into Avogadro number. That is what we have. Total concentration of the electrolyte is equivalent to the total number of ions which is going to generate. So, this is going to be concentration of the electrolyte into the Avogadro number. This is the volume element. Okay. Therefore, the charge that Ma plus ion transfers through the plane is going to be, now we are looking into the charge which is going to be transferred. It is going to be a positive charge Z plus into how much? That will be E. Ze is going to be the charge. Okay. So, Ze into the total number of ions present in the solution, that will be the charge associated with the M plus ions, and Z should be positive because we are looking into the positive ions. So, the charge which is going to be transferred to through this plane of passing through CD to coming into ABCD volume will be nothing but ZE, where Z is the positive charge, into the area, into the L, which is the volume, into the total number of ions, that is molar concentration into Avogadro number. Now, what is the total charge which is transferred? The total charge this is transferred when you have a current I flowing for an interval delta t is equal to I into delta t. Okay. The total current which is flowing through the system is I, and if the interval is delta t, then the total charge which is going to be transferred is going to be I into delta t. Okay. So, the fraction of the motion of the M plus ion can be given by the total number of the charge which is carried by the ZE type of ions divided by the total charge which is transferred when the I current flows at delta t time. So, this is going to give you the charge for the flow of I current through a interval of delta t, right. So, this is the total charge which is passing at time delta t, and this is the total charge of the charge of interest which is contained in the volume element ABCD. Okay. And I think there is a simplification here. You have E into Avogadro number equal to F. So, we have replaced E into Avogadro number as the Faraday constant into the L into A is the area and C is the concentration of the electrolyte. So, if we know the concentration of the electrolyte which is going to give rise to the lead solution, which is the cation of our interest, for which we are finding out the transport number. So, this is the charge carried by the ions which is passing the border CD, coming into this, diffusing into this solution to generate after time t. This is the region which we have. This is the region where you have the ions of interest Ma plus. So, the total number of ions charge species in the volume element is going to be ZE into Avogadro number into C into L into A. Z, if I multiply E with the Avogadro number, I get the Faraday constant. So, this is the total number of charges in the volume element, and this is the total charge we due to the flow of current I at delta time t. So, this is the total charge which is associated, and this is the total charge carried by the ion, positive charge ion M. Okay. So, this fraction gives you the transference number of the Ma plus ion. So, if I know the transport number of the Ma plus ion, then I can find out the transport number of the the X ion. That will be, if this T plus and T, because T plus and addition of T plus and T minus should be equal to 1. So, if I have T plus known, then I can find out the T minus, because 1 minus T plus should give you the T minus. So, if we know the transport number of the positive charge, we can find out the transport number of the negative charge in the of interest. Here it will be the X. So, similarly, we can do another experiment where you have the cations common and anions different, and do the movement of the charge across applied field and see what will be the T minus, and hence if you either of the T transport numbers are found, you can find out the respective other. If I know the T plus, I can find out the T minus. By 1 minus T plus will be giving you T minus. Similarly, if we do the experiment, instead of having a solution where you have a anion common, if I say take a cation common, that time I can find out the transport number of the anion. Okay. So, so here we have sorry, if here we have the anion common, so we found out the transport number of the cation. So, similarly, if I want to find out the anion, I have to keep the transport number of the cation common. Okay. So, if we have if we know the T plus, then I can find out the T minus, and since we know the transport number, we can hence calculate. If you see the expressions from the previous expressions, since you have T plus calculated, then you can respectively find out the values of in mobility, you can find out the values of the ionic conductivity and also the speed of the ions associated with each type of ion in the solution system. So, this is what the moving boundary method is. In the next class, we will take up what the Hittov's method and how we use the Hittov's method to find out the type of transference number associated with the electrolyte of interest. Thank you so much.